Okay. Today we will see two topics that are relevant today in energy and electricity. So the first one is power systems. And then the second one is Bender's decomposition. So the first one, you can find information in the Taylor's book. Okay, I will mostly follow this book. And the second one in Burge and Louveau book, which is Introduction to Stochastic Programming. Okay. So first, power systems. So these systems appear when you want to control the electric grid. And so you can represent the electric grid as a graph. Okay. So you have some nodes that you can number. Here 10 nodes. And then some nodes are linked by some wire. And you can transfer some electricity from one node to another one. Okay, and some node will receive power. And some node will consume power. And what you need to do is that you need to transfer power from the node that produce power to the nodes that consume power. Okay, so from that point of view, it looks like a simple max flow, min flow problem. What's tricky here is that the electricity obeys the laws of electricity, where you actually have that at each node, the voltage is a complex number. So what makes everything quite tricky is that you have the voltage at each node, which you can denote Vi, which will be a complex number. So you will have the real value plus imaginary value. Where does this come from? This comes from the phase description of here the voltage. So in electronic, what they like to do is, instead of saying that that this is some alternative current of intensity Vi and then of some cosinus I, what they like to do is to use the phase description where they actually see this. They represent the voltage as a complex number. and theta is the phase, basically the phase of the voltage. And so whenever you have two tension here that have the same frequency, if they have a different phase, you can see it with this different angle. And so when you have nodes with different phase, this will need to be taken into account when you transfer electricity between one node or the other one. Okay, so in power systems, you will need to take into account the phase at each node, and this phase will cause some nonlinearity, which actually makes this class of problems NP hard, because it makes them non-convex, because the phase will give you some sinus cosinus. And so what we will see in this lecture is that even if this is non-convex, we can do what we call relaxation, which means we will solve a different problem, which is convex, and we will see that even if it's not the same problem, it's a different problem, we can still infer some information on the original problem, and at least the convex problem will be easy to solve, while this power systems problem is NP hard. So I will not go into details on the electricity concept, because this is an optimization course. So basically, the only thing you need to know is that you have this, you have the voltage, which is some complex number that you can see either in polar coordinates or in Cartesian coordinates. Then you have P Ij. This is the power transiting from one node to another one. So here you will have P 8, 9, for instance, which is the power going from 8 to 9. And so if it's positive, it's in one direction. If it's negative, it's the other direction. And in fact, Pij and Pji are different numbers, because you may have loss. So you may send more than what he received. So the sum of the two is, in fact, it's non-negative, but it can be non-zero in the sense that you will have loss. So what you will have sent, which is positive, would be larger in magnitude than what J will receive, which would be negative. And so at the end of the day, this will be non-negative. And so P is the real power. And then you have something, I won't go into the detail, but you need to take into account Q, which will be the reactive power, whatever that means. So then, in this network, you will have, so the fundamental equation that we have to deal with is the following. You have Pij plus I Qij must be equal to and so Yij, this is just a constant called the admittance. Okay, so each link, for each link you have a constant complex, yes? Pij is the power going from I to j. So P710 would be the power going to 7 to 10, which is here a complex number because this is some alternative current, and so in the complex number, the angle is the phase, and the amplitude is how much power in watt do you send. And so there is a complex number y, which is called the admittance, which is some property of the line. But this is constant. But this is complex. And then you have vi, which is a complex number. Pij and Qij are not complex. I was talking about vi. So Pij, Qij are real numbers, but vi is a complex number representing the voltage and the phase at the same time. Sorry. So the complete problem is you need to find Pij. Yes?
What is, so the Pij plus Pji, it means that the outgoing power plus the incoming power is greater than?
No, it's so Pij is the real power. This is the reactive power. Okay, and here you have the imaginary unit. So this is a complex number. And here, complex number, complex number, complex number, and complex number. So we won't go into the electrical interpretation of that. Just take.
C? Is that what it is? C in Qij? Oh, I.
Okay, this is the imaginary number.
No, I was asking the first constraint Pij plus Pji.
Ah, yes. So yes, so this is the power that's going from I to j, that is sent from I to j, and this is the power received by j from I. And so when the power is sent, the sign is positive. When the power is received, the sign is negative. So if I is sending power to j, this will be positive, this will be negative. But because there is some loss, what is received is smaller than what is sent. And so the sum will be non-negative.
For every pair of nodes, there has to be more power sent. How does that make sense then?
But it won't be, actually this is not going to be a constraint of our problem. It's just some context, but it will be somehow implied by this, and if we ignore loss, it will just be equal to 0. Okay, so suppose you have n nodes. Pij will be some, so P will be some real matrix. Q will be some real matrix. And V will be some complex vector. And so then we have an objective function. We won't go into the details about what can be this objective function. Just assume it's something convex. Okay, we won't care about the objective function. And then you have constraints. So there is these constraints. If I do the sum of Pij over j, what is this? So it's so it represents the total power sent by I, and it will be positive if it's sending more power than it's receiving, but it can also be negative. So for the producer of powers, it will be positive, but for the consumers of powers, it will be negative, basically. But we will have basically some constraints on it. And same for Q.
And it's just due to like physical limits of the hardware?
Yeah. Okay. Exactly. And then we will have so this is a constraint for all nodes. So you have maybe different bounds for each node. And then for all link, what you have is so somehow this is the amplitude of this complex number. And this will be bounded by something. And this would typically be the maximum power that can go through that link. But usually the link don't have a maximum power, they have a maximum current. And so it will be the maximal current of the link multiplied by the voltage at I. Okay, because if you do current times voltage, it gives you the power. And so you have a constraint like this. Okay, so if you don't like electricity, you can forget about any electricity concept. Now we have the complete mathematical description of the problem we want to solve. So we can completely forget about the context and just do mathematics from now. So now the question is that problem convex? Suppose f is a convex function. Is that convex? Yes? So we can go through every constraint. These constraints, it's linear, yes? Linear. This one, second order cone. So it depends how we represent VI. So if we represent VI as being like the real part of VI, so let's say Ri plus this is a bad idea, AI plus BI, then this would be Pij square plus Q is that second order cone.
I mean, it is, right? I mean, it's composed with some, like, operation over the denominator.
Mm-hmm. But the issue is, normally in second order cone, here you have only one square. You have x1 square plus x2 square plus x3 square, for instance, smaller than t square. This is second order cone. Here you have the sum of two squares. So if you use that representation, it doesn't look like second order cone. Now if you use a different representation, which would be vi equals vi e of I theta. So now the variable are theta and vi. These are here the two real, imaginary number. Here you have two real decision variables, this one, and this is not convex. But if you use these two real variables to parameterize vi, then this become, then in fact, this is just a real variable, decision variable, and this is exactly, you need a square here, sorry. This is exactly second order cone. Okay, so depending on how you parameterize vi, you will either have this as a convex constraint or not as a convex constraint.
So when you use the second representation, what does it actually look like when you write it out? You just write down the magnitude of the exponential times the matrix.
So when you, so let's maybe write this differently. So let's call it Ri and theta I. So when you suppose that Ri, and so now what you would have is that Ri is some decision variable, and theta, I mean R is a vector of a decision variable, and theta is a vector of decision variable as well. And now when you have this, what this will become is times what? What's the module of this complex number in terms of R and theta? So basically, when you have the polar representation of a complex number, so you have the real part, the imaginary part. So you can either look at the real part, imaginary part, this is this representation, or you can look at what's the distance from the origin, this is r, and what's the angle theta. And then you have that the imaginary part and the real part are r cos theta and r sin theta. And then if you want to have this length, well, this is r, right? Because anyway, if this is a, this is b, if you do a square plus b square, you have r square cosinus theta square plus sinus theta square. This is 1. So this is simply r square, right? So here, this is convex, not convex. Okay, let's look at this constraint now. So in the first case, we have a square plus b square smaller than v bar. Is this convex? With this representation? Yes? It's linear or? Yes. Now, if we use the polar representation, what would this be? What is that? Is this convex? Yes, it's even linear. Okay, now this lower bound, with the Cartesian representation, we have ai square plus bi square smaller than bigger than the lower bound. In fact, we should have square here. Well, yeah. Is that convex? So this is just a constant. ai and bi are decision variable.
It's definitely.
So again, for the same reason for this, we have a convex function, but a convex function greater than a constant. Convex programming, one convex function smaller than a constant. When it's on the right side of the inequality, we prefer when the function is concave. Here it's convex. So in fact, this is not convex. Okay, last but not least, this one. So for this one, I will not look at what happens with this. Okay, very complicated expression, which is clearly not convex. What we can do is look at what happens if we plug in this one. Okay, so I won't do the algebra, but you should trust me that what you get is so first, the definition of Yij is okay. I keep the same notation than this book of Taylor. So with this notation, it's like that. What is J? What is B? It doesn't matter to us. Just think of it as the real part and minus the imaginary part. And so with this, you have that Pij equals So when you expand this, the real part you get is this. And then you have some imaginary part as well. But we won't go into the details. You can check in the book. So if you look at this, do you think it's convex? I try to everything on one line. Let's define y here.
The asterisk is transposed, right?
Yes, it's the conjugate.
Because it's convex. Because it's
Complex, yes. So is that convex? It's not a convex constraint in I in J. So because it's an equality, for this to be a convex constraint, it means that this expression should be what? Convex, concave, linear? Linear. So is this linear in theta and this would be the R in my representation, right? This would be Ri. So is this linear in R and theta? Clearly not, because you have sinus, cosinus. Okay? Okay, so given this, how do you think that the electricity goes through the grid? How do countries optimize, or power line companies, how do they optimize the power networks, given that they have these equations? They need to choose how they represent VI. So this one clearly doesn't seem very nice. You have many non-convex constraints. At least with this one, you only have one non-convex constraint there. With this one? No, with this one, this is SOC, and this is linear. The lower one as well. And these are linear. So with this one, you only have this one as non-convex constraint. And so because of this, what is used a lot in practice is to use this one, but then take some approximation to make this linear. And the approximation are first, let's assume that Ri is more or less 1. And second, let's assume that Gij is way smaller than Bij, in such a way that you can even consider that G and J, you can replace it by 0. And so with this, you have pi ij equals which is much simpler, but still not convex. So now they do a last assumption. They assume that the phases are very close to each other. And because they're very close to each other, they know that inside this sinus, this will be a number very close to 0. And so they do a Taylor expansion of sinus. Say, okay, sinus of x if you do the Taylor expansion around 0, you have sinus of 0 plus cosinus of 0 times x. If you do first order Taylor, so you have x. Say approximate. And so and now this finally is linear. Okay, so what is used a lot in practice to solve power systems is to use this representation and then do these approximations such that this constraint becomes this. And now all the constraints are linear. And if the objective is quadratic, it's just a QP. So it can be solved extremely efficiently on extremely large network. If the objective is linear, it's even faster. Any question up till now? Yes?
So you say once you eliminate the nonlinearity from the sine and cosine,
Yes?
you said it's linear?
This
Equality constraint?
This is an inequality between P, theta I, theta ij.
So what happened to all the other variables? Oh, I see. There's all these like.
Yeah, you say GI is 0 and R is 1.
Where are these are just physical assumptions?
Yes.
Okay.
It made sense for electricians, let's say. So basically, yeah.
What is like the theta I is approximately theta j? What does that mean? Like the amplitude for the phase?
The phases are very close to each other.
From node to node?
Yes.
Repeat the questions.
Sorry. So what does that mean? So that means that basically two nodes that have a links between each other have a very, very similar phase. So we don't take the assumption that they are equal, because otherwise this would just be 0. But that would be a bit too much of an approximation. But because you know they are close, what you can do is say, I take the first order Taylor approximation around 0. So basically saying they are equal, it would be the same as saying the 0 order Taylor approximation, just taking 0. And taking first order Taylor approximation, at least it's linear and it's everything we need.
So are these assumptions reasonable because you only send like a small amount of power between stations or something? Or what is the...
It's reasonable because in practice the phase are quite small. The phases are quite close to each other.
So the takeaway is like if we know from physics or something that we can linearize things by using physical assumptions.
Exactly, yes. Yeah. Sometimes when you need to convexify, you can try to see if you know a bit more about the problem and do these things. So that's the first approach. Now there is a second approach. So I mean, one approach is also using a nonlinear solver, but then it doesn't scale very well. And then if you use a nonlinear solver, okay, you're solving the exact problem, but then you're never sure to find the optimal solution because they are just local solver. So here, even if the problem is approximate, at least you will find the optimal solution of the approximate problem. But the approximation is a bit rough, and so it's not so accurate sometimes. And so there is a second option, a second approximation, which is more subtle, and that doesn't use any physical assumption. And this is a very common trick that is done in convex optimization, and it's done in many different areas. And in in many areas, this trick is used with real numbers. And what's interesting here is that you actually use it with complex numbers. So what you do is you look at this constraint again, and then you realize that here you have this vector v of complex number. And here you only have bilinear term in v. So basically what you have is you have vi plus vi vj. So you only have bilinear terms in v. And so a classical relaxation when you have bilinear terms is to consider the matrix, the following matrix. So if you do vi conjugate, what you have is you have the matrix with v1 conjugate, v1 v2 conjugate, v1 vn conjugate, so if you look at this matrix, these two are entries of this matrix, right? So if you name this matrix big V, this is Vii, and this is Vij. So don't confuse the small v and the big V. And you can see two things about this matrix. First, this matrix is Hermitian because this is the conjugate of this, because V1, Vi, Vj conjugate. If you take the conjugate of this, it's Vi conjugate Vj.
I can't really see the subscripts, but you just did the outer product, right?
Yes. So this is 1, 1, 1, 2, 1, 3, and so on. 2, 1, 2, 2, 2, 3. So this is, you have V1, Vn. You take the product of this with V1 conjugate, Vn conjugate. And so you have this n by n matrix, which has rank 1. So you see that V is Hermitian. It has rank 1. And in fact, it's positive semi-definite, I mean in the Hermitian sense. Okay, because a complex matrix being positive semi-definite is not so clear because you can get complex number. But in Hermitian matrix, it does make sense. And in fact, we talk about it in the fourth lecture. There is what we call positive semi-definite programming, where you're looking for matrices that are positive semi-definites. You can also do that for emission matrix. So somehow you can, instead of looking for these vectors vi, you can look for this big matrix V. And then what you do is you have, so okay, minimum, so looking for again P, Q, and then this big matrix V. Okay, you hope that your objective is expressed in bilinear terms of V. Otherwise, you have Pij plus I Qij. And then here you simply have equals to Vii minus Vij. So now this constraint is linear. So these two constraints remain the same. The fourth one becomes Pij square plus Qij square.
So you just change the decision variable from two vectors to one matrix, right?
Yeah.
From a product matrix.
Yes.
So that's how you linearize it.
Yeah. It's very weird when you see it the first time, but it's extremely common, this trick. And now, this constraint also becomes convex, because Vii is a real number. Because when you have an Hermitian matrix, so when you have your Hermitian matrix, your decision variables are here. You have some real numbers. Here, you have some complex numbers. And here, this one, you know them because it's Hermitian. So in fact, when decision variable is an Hermitian matrix, what you're looking is, here you're looking for n real numbers. And here, in this triangle, you're looking for some complex numbers, either in polar or Cartesian coordinates. But so this is just a real number. Okay, so then this is a second order Cones constraint there. Very good. And this guy, it is Vi square smaller than Vii smaller than Vi square. What is this constraint? So now this is SOC, this is linear, and this convex, linear, SOC. These two are just constants. And VII, it's on the diagonal. So it's a real number. So just a real decision variable. So this is just bonds on some real decision variable. So this is linear. Okay. But then you need to say V is belongs to, let's say it's Hermitian PSD. And V has rank 1. Okay, is this formulation convex? So this is linear, this is a convex constraint, this is linear. This is a convex constraint because the cone of Hermitian PSD PSG matrices is convex. So this is convex. This is not convex. The set of rank 1 matrices is not a convex set. Okay, so we have done a whole reformulation, but not convex. Is it surprising that we failed? Not at all, because I said at the beginning that this problem is NP hard. So there is no way to do a reformulation into a convex problem, because convex problem we can solve them. Or maybe if we do a reformulation into a convex problem that has exponentially many variables or exponentially many constraints, is still not an efficient way to do it. But there is no way to reformulate an NP-hard problem into a convex formulation that has a small number of constraints and variables. So this is not surprising that we failed, but it might still be interesting. Because here we had to linearize this weight constraint and we lost a lot in accuracy. And here we only have one remaining constraint that is non-convex. And somehow this one, maybe what you can do is we just drop this constraint. We forget about it. So let's just say you solve the problem, but without this constraint. So if you do that, what's interesting is, yes.
So the Pij plus I Qij, right? This is really, it's going to, when you actually optimize, you're going to optimize for two real number constraints, right?
Yes.
Okay. Just basically the scalar components.
Yes. Yeah. Yes.
It's like a two by one vector, essentially.
Exactly. So this is one inequality in the complex number, and in fact it will be two equalities for your solver, which will be in the real numbers.
So we always do that. There's no way to directly optimize with complex. We always just convert to these vector.
There are some solvers that support complex input. SDPT3 is a solver that supports complex input. So you can optimize over complex Hermitian matrices, for instance. And the whole solver is written, I think, for complex numbers. And so it does operation with complex directly because it's written in MATLAB, so it's possible. There are some Julia solvers as well that supports complex numbers. Hypatia, I think, that's developed at MIT. It supports complex numbers. But most solvers, they don't. Okay. So now, suppose the following. Suppose you solve this problem. Okay? Assume you solve this problem without the rank 1 constraint. And suppose you find some matrix V. Okay? It's a Hermitian PSD, so you can take its decomposition. So by taking the decomposition, you might see that it's equal to some V. You might be lucky, and even if you didn't put the constraint V is rank 1, the solution is rank 1. So what's happening in that case? What can you conclude? So you solve this problem without the rank 1 constraint.
You just got the answer for free, right?
Yeah. And so in that case, this is the V you're looking for. And so in fact, is that V that you find here, is this an optimal solution? If you combine this V with the P and the Q you had, is this an optimal solution of the initial problem? This one. Yes? Why?
I mean, the only thing, you just said that if you solve it without the constraint and you find that it satisfies the constraints just by checking them afterwards,
Yes.
then of course it's a solution to the original problem.
Exactly, yeah. Very good. Now suppose that it's rank 2. Sorry, so the answer was yes, this would be a feasible solution because, for example, you can just plug it in all the constraints and you can just see that they satisfy all the constraints of the original problem because they are here, and the rank 1 constraint is in fact verified. So in fact, you respect all the constraints of the original problem. But if it's rank 2, what can you say? So it seems you might be kind of stuck, but there is one thing you can say. Suppose that it's rank 2, but then, like, suppose the minimizer here tell you, like, the minimal objective is, so f of p, q, big V, suppose it's equals to 10.4. What can you say about the objective of the original problem? Do you think it's possible that it's bigger than 10.4 or that it's higher than 10.4? Do you think you can exclude one of the two cases?
It must be greater.
Why?
Because this is relaxed.
Exactly.
Yeah.
So by removing the rank 1 constraint, you do what we call a relaxation. So if you think about it, the function f is the same. But the feasible set because you just remove one constraint, so you had this formulation which was completely equivalent, and then you remove a constraint. So because you just remove a constraint, the feasible set is a superset of the original set. Okay, so it's like you minimize some function. It doesn't even need to be convex. If you minimize some function over this domain, if this is your domain, then the minimizer is this. When you do a relaxation, it means you only make the superset larger. So for example, suppose the new feasible set is this, then you've got a new solution which is here. But when you do a relaxation, all the previous solutions are still solutions. You only have new solutions, right? So because you can only have new solutions and all the previous solutions are still solutions, the minimum you get can only get lower. Okay? And so it means that 10.4, it's not the optimal objective value, but it's a lower bound to the optimal objective value. Okay, just like when we view last week duality, and we saw that duality was a way to get lower bound, you can also get lower bound by solving relaxation. So you take your problem, you have a constraint that is very hard, you just drop it, you solve your problem. When you've solved your problem, you know that what you obtain is a lower bound, so that's information. And if you're lucky, maybe the constraint you dropped because it was too hard, maybe it's respected just by chance. Okay, this is a very, very common trick in optimization. You have a complicated problem and you were like, oh, if only the constraint was not there, this would be easy to solve. Just remove it and solve it. because in optimization you quickly have the situation that with this constraint it would take you millions of years to solve, but without the constraint you can solve it under a second. Then do it. It will actually give you information very quickly, and you can do things with that. So it's often very useful to just fall back on what's easy to do. And then once you've solved this formulation that is sufficiently solvable, try to see what you can deduce. Okay. Okay, so we won't have time to talk about Bender's decomposition, but that's okay. Let's just finish this. So in practice, some people don't like this because even if it's a convex problem, the number of variables grows a lot. Because here, suppose you have 1 million nodes. Maybe not 1 million nodes. Suppose you have 1,000 nodes. Then here the number of complex numbers here grows quadratically. So if you have 1,000 nodes, here you have almost 500 million of numbers here. 500,000, sorry. So if you have millions of variables, when you solve an LP, it's okay. But if you solve an SDP with millions of variables, you will suffer very badly, okay? And that's a bit unfortunate because, in fact, like even if you had, like you could tell me, oh, but hey, P and Q, they also have a quadratic numbers of variables, right? Because P, you told me that P was n by n. But in fact, you can, P is not really n by n, because if you have a sparse graph, you don't need the P variables for all the nodes that are not there. So if you have millions of nodes, maybe you only have 10 millions of edges, right? You don't have 1 million square edges. And so P and Q are still quite small. Even if you have millions of nodes, P and Q can just be like 10 million entries. But then here, we'll have 1 million squares. So it's not even, it doesn't fit, like the problem doesn't even fit in memory. So that's a big issue because you have a lot of sparsity in the problem, but you cannot exploit that. So there is some way to exploit sparsity in SDP using chordal graphs and so on. But there is a way to do yet another relaxation that will make the sparsity be exploited automatically. So when you say a matrix is SDP, you say a matrix like even in the real case, when you say P is positive semi-definite, this is equivalent to saying that all principal minor minors are PSD. Okay, so what do we mean by that? By these minor things. So you just take your matrix and you take submatrices. But submatrices align with the diagonal. So for instance, you take a subset of indices and then you index with the same subset for the rows and columns. So suppose you had matrix with 4 rows and 4 columns. You take this subset, let's say, and so you get these entries. If you take this 2 by 2 matrix, if this matrix is PSD, this one should also be PSD.
What is the
Yeah, no. This is 1, but you could also, we can take any subset of index that you apply on both sides and you take the submatrix.
Any subset of the index?
Yes, so you take PII for any subset of indices I, and this is a principal minor.
But it has to be a square, obviously.
Yes. Okay, so, but in particular, if you take the principal minor, which take 1 by 1 matrices, so when the number of elements is 1, what does it give you? It gives you P11, P12, and P22, and so on. And what you know is that these guys are PSD, but 1 by 1 matrices PSD just mean non-negative. If you take length 2, then you have P11, P12, P21, P22 is PSD. And you have that for all PII, PIJ, PJI, PJJ is PSD. And you have that for all IJ. That's with 2 by 2 minors.
So then this is all
And so when you say that the 2 by 2 matrix is PSD, it means it's equivalent to two things. First, it's equivalent to the combination of two things. The trace is non-negative, so PII plus PJJ is non-negative. And second, the determinant is non-negative, which is PII, PJJ is greater than PIJ, PJI. Note that this, because we already know that the diagonal entries are non-negative, this is not useful. It doesn't give you any new constraints. But this one is interesting. Is it convex? Because the hope is that, okay, if we only, like this is equivalent, but if we only say only principal minors 1 by 1 and 2 by 2, and then we stop, we don't look at 3 by 3, 4 by 4, and so on, then it's only an implication on that side. And so it means we drop constraints again, but it just means we will have a relaxation. But at least now maybe we won't have to solve an SDP. Let's hope. Just need to see what is that thing. In fact, because we know that our matrix is Hermitian, then PJI, this is P ij. This is the conjugate of Pij. And so what we have here is Pij times its conjugate. And so it means it's the length of Pij. So we have the real part of Pij square plus the imaginary part of Pij square smaller than Pii, Pjj. Okay, because this is very important, I think I will write it more clearly. So the real part of Pij square plus the imaginary part Pij square smaller than Pii Pjj. Is this a convex constraint? So here we haven't really discussed how we represent the off-diagonal entries of P. So here suppose that you represent the off-diagonal entries of P in the Cartesian way. So it means you would say that Pij is A ij plus Bij for some real numbers. It's quite bad to, yes, let's call it im, like in Julia. This is for all I different than j. So is this convex? So this is a real number square plus a real number square. So for now it looks like second order cone. But then what do you have here? Pii plus Pjj times Pjj. Is this convex? Very good. So this is rotated second order cone. Okay, so this is convex. And this is rotated second order cone, which is easy, in fact, to reformulate into second order cone. And so it means that if we only take the first two minors, we have a second order cone programs. Okay, that's better than SDP, but does it solve the sparsity issue? Do we still have millions of variables if we have 1,000 nodes? So if there is no link between I and j, suppose there is no link between I and j. So you don't have this constraint. If there is no link between I and j, it means Vij doesn't appear in this constraint. It means Vij, the only place that Vij appears is in this constraint. Yeah, here P is V. You should say V. So if the only place where V appears here is in this constraint, does it make sense to include it in the optimization problem? Because there is a trivial solution for V that always works. Because this one is non-negative, this one is non-negative anyway, because they should be for the rotated second order cone, but they are. You can always take Vij equals 0. That's always a solution. And if Vij is not used in this constraint because there is no link between I and j, you can just take Vij equals 0. This will be optimal all the time. So it means for all the links that are not there, you can get rid of Vij. And so the number of Vij that we will have to consider is exactly the number of links you have. So now you can solve if you have millions of nodes and 10 million links, you just have 10 million variables. That's it. So the advantage of rotated of the second order cone formulation is not only that second order cone is easier to solve than SDP, but also because you exploit sparsity very well. With no abstention on the graph. For the SDP case, you will have that. You have to have the fact that the graph is chordal. If it's not, you have to do some chordal completion. So you might not completely exploit the sparsity. Here it's exactly the number of links. But the issue is that it's a relaxation again. But there is something a bit particular to observe. Is that even if it's a relaxation, notice that we have a lot of freedom on Vij, right? we have a lot of freedom on Vij. We can see that we can just put it to 0 if it doesn't appear in these constraints. And so for the same reason, you can argue that, in fact, it's always good to take Vij as large as you can. And in that case, you will have equality here. And once you have equality here, you actually have that the determinant is 0. So you can argue that in an optimal solution, you can always take that, in fact, these 2 by 2 matrices have rank 1. And so it means that Vii, Vij, Vji, Vjj, they are equals to Vi, Vj, Now, there is always a little bit of freedom when you do this decomposition. Here, there is not a unique way to decompose. You can always kind of rotate your numbers. So whenever you solve, whenever you have, suppose you solve, you have your V matrix. Then by looking at the diagonal, you directly have what should be the norm of your Vi, Vj, and so on. And to find the phase, like in this case, if you have the phase of Vi and this matrix here, you can determine the phase of Vj if you assume this is rank 1. And so basically, I will have to cut it short, but the idea is that in the case where your graph is a tree, because you know that these matrices are rank 1, what you can do is take any node. Let's say this is 1. You choose any phase for this node, because the phases are only relative anyway. So suppose you say this one has phase 0, and then for each node, you will look at the corresponding 2 by 2 matrix. And by looking at this matrix, you can determine the difference of the 2 phases. And so you will find the phase of this one. And then you do that for every node. And then you will determine a feasible solution for the original problem. And so in the case of a tree, the relaxation is always exact. So first, when you solve the stock relaxation, what you will find, even if you don't have all the needed constraints, is actually Hermitian PSD. But also, this Hermitian PSD is also rank 1. So the 2 constraints you drop will always be satisfied in the case of trees. Now, if it's not a tree, you have cycles like this, then it might not work, because if you do this same procedure, okay, you find this angle for this one, the angle for this one, the angle for this one like this, and then the angle for this one like this. Then if you look at this, the choice of angle you have here might not match with the 2 by 2 matrix you have for these two. So the reasoning only works for trees. Okay, so, but in any case, even if it's not a tree, you have a relaxation, so at least the value of the objective function will be a lower bound. And that's everything I wanted to say. Any question?